Hello and welcome, dear listeners, to episode 57. Today, I'll be continuing my series on the plant kingdom by exploring the next two major divergences in the plant lineage. So far in this series, I've talked about green algae, which represents the ancestral branch of all land plants. And I've talked about the bryophytes, which were the first true green land plants that emerged from the slimy primordial muck of the green algae. But these bryophytes, the liverworts, the hornworts, and the mosses, they're all simple plants, lacking vascular tissue, and they're dependent on a water matrix for reproduction. Because they lack vasculature, the bryophytes require diffusion to move water and nutrients through their bodies. Diffusion is a relatively weak force that can't move water very far, so the maximum size of the bryophytes is limited. About 425 million years ago, during the Silurian period, the first Lycophytes appeared, and these were interesting for several reasons. First among them being the fact that these plants had primitive vascular tissue. They had an internal cellular physiology that created the first basic pipes, or tubing, that optimized water flow and sugar transport throughout the plant. These water pipe structures, which would become a fundamental aspect of pretty much all of the vascular land plants, are called tracheids. They're long, columnar tubes with tapering ends, shaped kind of like a toothpick, but just orders of magnitude smaller. These little toothpick-shaped columns are also studded with little pits, or holes, so that when you have billions of these little tracheids all aligned vertically and bunched up together, their sum total cell wall tissue will create a hugely porous mass that can conduct water extremely well. So I talked about this in a little greater detail in episode 50 on plant hydration. But basically, there are a confluence of factors, like the various qualities of liquid water and the form of the tracheids, that allow them to efficiently move water vertically against the force of gravity. For sugar transport, they evolved sieve tube elements, which are columns of large cells, almost entirely empty of organelles, with their connecting cell walls perforated by holes that allow this sugar-rich water to flow through. Equipped with these primitive tracheids and sieve tubes, the early Lycophytes found that they could transport water higher up off the ground, which opened the door for them to grow larger than any plant before them had ever been able to grow. But don't get carried away with your imagination. The early vascular structures of these early Lycophytes were, as I said, really primitive. They were simple, unrefined. And while they could move water better than moss could, their vasculature was still relatively weak and low complexity. For example, a defining feature of the Lycophytes are their microphylls, which are thin, tiny leaves possessing a single vein running down their center, with diffusion moving water and nutrients out from that central vein into the surrounding leaf tissue. However, evolution doesn't stop. This simplicity was not bound to last forever. Over millions of years since their first emergence, these early Lycophytes evolved and they adapted greater complexity, such that the world became covered in the sprawling forests of these massive Lycophyte trees. The order Lepidodendralis and Sigillaria thrived during the early Carboniferous period, growing up to 30 meters tall and 1.5 meters wide, and spreading out to cover more ground and expand their range. This spread and growth lasted for more than 100 million years, spreading massive tropical Lycophyte forests across the European and Asian continents. But about 300 million years ago, the climate began to change. The world got drier and colder, and this led to the Carboniferous rainforest collapse, which saw the widespread fragmentation and reduction in total size of the world's forests. The golden age of the massive Lycophyte trees came to an end, and they began dying off. In the modern day, the extant Lycophyte species are all relatively short and small compared to the more recently emerged lineages of trees and tall bushes and plants like that. The Lycophytes can be separated from algae and bryophytes because they possess vascular tissue, and this allows them to transport water higher up against the force of gravity, and it enables them to grow taller. They can also be separated from bryophytes due to the fact that their sporophyte generation is dominant, not their gametophyte generation. Now on the other hand, on the other end of the spectrum, the Lycophytes can be separated from the more complex vascular plants like gymnosperms and angiosperms because the Lycophyte vascular tissue is relatively simple. Where the gymnosperms and the angiosperms have sophisticated cellular mechanisms for transporting water, the Lycophytes just have a simple structure called a protostela, which is a vascular tissue composed of a single column of xylem with a layer of phloem wrapped around it, running through the center of the tissue like a stem or a leaf. There are several types of protostela that exist in the various lineages of Lycophyte, each with its own different structural shapes and morphology and functional advantages. The simplest protostela is called a haplostela. It's composed of a simple cylindrical column of xylem wrapped in a simple tube of phloem, and it also typically has a layer of endodermis that's wrapped around that, kind of like saran wrap. Another type of protostela, common in club mosses, is the Actinella, which is similar to the haplostela, except that instead of the vascular tissue being a simple cylindrical column, the Actinella has lobes, bends, grooves, and folds. The structure is a lot more dynamic and asymmetrical than the haplostela. The phloem layer in the Actinella is generally thinner, and the xylem is much more irregular. The third type of stela is the plectostela, which is a little weird. The xylem grows in a column shape like the simple haplostela, but the phloem isn't just simply wrapped around it. The phloem penetrates the xylem and cuts through it, forming a series of these parallel plates or parallel sheets of phloem that transverse the xylem column. Earlier I mentioned club mosses. These are perhaps some of the more common kinds of Lycophytes. These plants have lobe-shaped leaves, or leaves that don't appear to protrude like the typical leaves you'd see on an oak tree or something. Consider the club moss Diphasiastrum digitatum, or the fan club moss. These plants have flat, plastic-looking leaves that extend outward with a dichotomous branching pattern. At every node of branching, the main stem divides into two smaller branches. The main stem splits once, twice, 5 times, 10 times, producing a lot of branches that all radiate outwards like green fingers. It's because of their fan-like appearance that they're called fan club moss, and it's because of their dichotomous branching that produces these Y-shaped joints between the branches and the Y-shaped branch tips that gives them their colloquial name, crow's foot. Another species is the Lycopodium clavatum, or the ground pine, which literally looks like a tiny little pine tree growing out of the forest floor. They have a main stem that's apical dominant, so it's taller than it is wide, and their branches have little overlapping leaves that look like pine needles, and they have a simple branching structure. They really do resemble the branches of a pine tree. Some of the branches have sporophyll leaves protecting the sporangia, the reproductive structure that produces spores, and when it's time to reproduce, these branches are held straight up, high into the air. The sporophyll's leaves will dry out, and they'll get degraded by the wind, and physical disturbances like an animal walking by or kind of chewing on the plant. Its fur will brush up against it and just mechanically destroy it. When this happens, the spores get released. They float on the wind and land somewhere else, and if it's habitable ground, they'll germinate and grow into a new individual. These tiny ground pine Lycophytes have a close relative called Lycopodium obscurum, which is a less widespread cousin species that grows 4 to 5 times as tall as the Lycopodium clavatum, with a more complex branching pattern, but the similarly short, thin leaves that really captures that pine sapling look. A lot of other club mosses have this similar general appearance, with simple branching structures, a mature form that's only a few centimeters tall, and a body plan composed of a single stem with little to no branching. The stem itself is covered in small, thin leaves that look to the naked eye almost like fuzzy green hairs. Some of these species include the simple Lycopodella inundata. There's a species that's thicker and fuzzier, called the Hesperia salago, or the northern fir moss, and the equally fuzzy but moderately taller Hesperia lucidula, or the shining fir moss. So there are these club mosses and the very closely related fir mosses. And if we move out evolutionarily a little bit, there's the Selaginella genus of spike mosses, then the Isoetes genus of quillworts. I mentioned the Lepidodendrales earlier, the ancient Lycophyte trees that were the dominant tree life form on the planet more than 300 million years ago. And well, it's believed that much like the birds are to dinosaurs, the closest living relatives of these ancient plants are the quillworts. This is generally believed to be the case because of the Acoetes beestoni samples taken from Permian-era rocks, representing some of the first known quillworts. These samples demonstrate several interesting traits shared with the giant Lycophyte trees, including the growth of modified shoots that were actually used as roots, and the growth of wood tissue and bark as an outer protective layer. All of these Lycophyte groups I just mentioned are part of a larger group called the Fern allies. The so-called Fern allies are fern-like plants. They have a similar morphological pattern to their leaf expression to true ferns, and they also have a dominant sporophyte generation that reproduces with spores. The other fern allies include the Silotopsida, or the whisk ferns and the moonworts, as well as the Equisitopsida, or the horsetails and scouring rushes. The Silotopsida whisk ferns are small shrubby plants with rhizoids instead of roots, and they don't have any true leaves. Instead of leaves, they have these weird discolored bulbous protrusions called enations. The Botrychium moonworts are a little more complex, as they can grow somewhat thick leaves and true roots, but they depend on a symbiotic relationship with fungi to obtain all the nutrients that they need. Another Silotopsida group is the Ophioglossosea family, or the adder's tongue plants. These are really strange-looking plants with a single large leaf, and a large sporangia that looks like the tip of a rattlesnake's tail, but it's slender and green and on the end of a plant instead of on the end of a snake. Then there are the Maritiidea ferns, which are relatively huge. The Maritiidea ferns grow thick stems and thick branches with big leaves, some of the biggest leaf fronds of any fern ally, or of most ferns for that matter. The other group in the fern allies is the Equisitopsida, or the horsetails and the related species. The horsetails are really interesting plants because they show quite a bit more structural complexity than the first mosses that I described. These have stems that grow in squat, cylindrical segments, and beginning a few centimeters off the ground, the junctions between each segment start to express a whorl of leaves. The leaves are thin tubes, like tentacles or spokes, each vascularized by a single vein. As the plant grows taller and the top of it gets higher off the ground, the horsetail's leaves will grow longer, which gives them that characteristic horsetail shape that they're named after. Although personally, I think that they look more like a caveman's club than they look like a horse's tail. Anyway, each segment of their stem possesses an intercalary meristem, which means that growth can occur here in each segment, and not just at an apical meristem at the tip of the stem or at the tip of the branches. Although every currently living species of horsetail is purely herbaceous and relatively small, there are extinct species of horsetail that could grow wood through secondary growth, and grow to become 10 or more meters tall. So the club mosses, spike mosses, and quillworts are all Lycophytes. They're fern allies, which means that they're basically just simple primitive cousins to the ferns. Then you have the whisk ferns, the horsetails, and the Maritiidea, which are also part of the fern allies, but they're in a group called the Usporangiate ferns. Where the Lycophytes are like cousins to the true ferns, the Usporangiate ferns are like siblings to the true ferns. These are grouped together because they share a similar developmental strategy for their spore-producing structures. In these Usporangiate ferns, they have an entire group of differentiated cells that will develop and grow into the sporangia. This differentiates them from the true ferns, called the leptosporangiate ferns, because they will produce their sporangia structures from just a single epidermal cell, instead of a whole group of cells. So basically, boiling all of this down, the clade that's known as ferns refers to both the Usporangiate and the leptosporangiate ferns, but only the leptosporangiate ferns are called the true ferns. I want to talk about the evolution of ferns, but first I'll talk about them from a more general perspective, so you can see kind of what they evolved into and what their evolutionary process kind of involved the development of. Ferns are like vegetable frontiersmen, or photosynthetic pioneers, if you will, of suboptimal habitats that seed plants and flowering plants might find stressful. In these kinds of habitats, the ferns are able to outlast and outcompete the other kinds of plants, and so in these areas they tend to dominate. These areas include wetlands like the marshes and swamps, the crevices, pits, and other dark areas in mountainous terrain and dry desert, the humid, shaded areas of tropical, temperate, and boreal forests, and in the trees themselves, where the ferns manifest in a huge variety of epiphytes. The fern stem is composed of tissue that's a little more dense than you would find in a typical herbaceous plant. Many ferns possess stems that are composed of a semi-woody tissue, and this gives them the strength to grow to extreme heights for a fern, like in some cases 20 meters tall. Smaller ferns, like shorter ground-dwelling ferns and the epiphytes that grow on trees, have horizontally growing stems called stolons. These stolons will creep along a tree branch or along the ground, where they'll establish new nodes. At each node, the plant starts to grow roots or rhizoids that either penetrate into the soil and tap it for water and nutrients, or in the case of rhizoids, that anchor it to the tree or to whatever surface it's growing on. The roots work just like the roots of seed plants, but only in the sporophyte generation. Remember that ferns are sporophyte dominant, and this larger sporophyte generation will have legit root systems. But the gametophytes, the smaller, non-dominant generation, will only grow rhizoids. These rhizoids are much thinner, they're more fibrous, and much shorter than the actual root systems. The rhizoids only grow relatively shallowly into the soil, and this just provides a degree of mechanical anchoring. And in many cases, like for epiphytes, the rhizoids don't absorb nutrients, but instead they work, as I said, to anchor the fern onto the tree branch. From these nodes where the root or the rhizoid systems form, or off of the stipe that branches off the stem, the fern will grow leaves. These leaves will emerge from the fern's body as a growing mass of leaf tissue that's tightly coiled up into a ball, often called a fiddlehead because of its similar appearance to the end of the musical instrument. Through an unfurling mechanism called circinate vernation, this leaf ball loosens up and rolls out into a flat, mature leaf form. The leaves that grow off the stipe are called pinnae, and these are complex leaves with smaller lobes called pinnules that are organized along the leaf edge like teeth in a saw. Most of the fern's leaves are trophophil leaves, or leaves that are purely for photosynthesis, conducting sugars and enabling growth. The minority of a fern's leaves are sporophyll leaves, and these are fertile leaves that are involved in reproduction. In many species, they look exactly like the trophophil leaves, and they can still conduct normal photosynthesis. But in some fern species, they might be smaller or paler due to less pigment, and so they would also have a lower capacity for photosynthesis. On the underside of these sporophyll leaves, and this is what really makes them different, they harbor the sporangia, which grow as little globs or spheres called sori, which are arranged in rows or groups. So the sporophyte generation grows these sporophyll leaves, which are fertile leaves that possess masses of granular sporangia along their undersides. These sporangia produce and release haploid meiospores, which can be pushed by the wind or blasted some distance away by a release mechanism. For example, a lot of sporangia have a protective coating called an indusium, and this indusium can dry up and shrivel until the internal pressure that shriveling creates will cause it to rupture, and the force will throw spores some distance away, kind of like shrapnel from a little mini explosion. These spores will land somewhere far from the parent plant, and they'll presumably germinate and then grow into a new haploid individual of the gametophyte generation. The gametophyte generation of most ferns is really small and stubby. It looks like a moss or like a liverwort. The photosynthetic body form is the prothallus, which is just a kidney-shaped or a globular structure with a width and a length typically less than 9 or 10 millimeters. The photosynthetic prothallus is typically composed of just a single large cell, but the gametophyte form has other cells, it's still multicellular, and these other cells do other things. Namely, they have gamete-producing structures that they use to reproduce, because they are the gametophyte after all. The antheridium is the male sex structure, and this produces flagellated sperm, or sperm with flagella. To get the sperm into contact with an egg, the sperm is released into water, either groundwater from flooding or rain or a river or whatever, or raindrops that splash and launch little particles a short distance. However it happens, the sperm makes it to the archegonia, which is the female sex structure. Like the other plants that I've talked about so far, the archegonia is shaped like a flask or a vase. The sperm flows in through the top, and it goes down through the tube, through the neck, to the open space at the bottom, where the egg is stored. This initiates fertilization, creating a sporophyte individual that will grow into a larger, mature fern. Okay, so earlier I mentioned the Usporangiate and the Leptosporangiate ferns, and their evolution. I talked at length about the Usporangiate ferns. They're the Horsetails and Whisk ferns, and the Maratiidea, and all of those. But now I want to dive into the evolution of the true ferns, of the Leptosporangiate ferns. These first emerged on the planet sometime in the Devonian period, some 360 million years ago, but many of the earliest species have gone extinct. Most of the currently existing fern species originated sometime in their lineage within the last 200 million years, during the so-called Great Fern Radiation in the late Cretaceous period. The first lineage to appear that would persist into the modern day was the Asmundaceae family, which is presently quite small, with less than 25 known species, although the individuals in most of these 25 species tend to grow relatively large for a fern. They grow very tall or very fat, with thick stems and big leaves. After their divergence came the Hymenophyllales, or the filmy ferns, which emerged sometime in the late Triassic, around 200 to 250 million years ago. The Hymenophyllales have diversified into about 650 species, the vast majority of which are confined to humid and wet habitats, like the Pacific Northwest in North America, and the more humid Atlantic coastlines of Europe. These are habitats characterized by a lot of rain and fog, and in some places there are waterfalls where water is being constantly thrown into the air. The humidity around a waterfall is relatively high compared to the rest of the local environment. As a result, these filmy ferns are typically covered in a thin film of water, and that gives them their name. Basically, they typically grow in places where there's a lot of water, so they're not often exposed to dry air or drought conditions. They haven't really evolved any major defenses against water stress. They don't have stomata. They have a very small cuticle, or no cuticle at all in some species. Their fronds are often just a few cells thick, so dry air would easily suck the moisture right out of them. Although, not all of these Hymenophyllales live in humid, wet areas. Some of them have diversified a little bit into more temperate areas, and they're a little sturdier. They have a little bit better resistance to drier, colder climates. The next divergence in the Leptosporangiate ferns are the Gliacaniales, which are found mostly in tropical regions, like the island environments of Oceania and the Pacific Ocean. The Gliacaniales are wildly diverse, with species that look like tiny ferns, big ferns, and even that look like palm trees. Because these ferns are so diverse, they aren't easily tacked down into a single clade with a nice, clean description. Instead of being a discrete clade with a group of shared traits, the Gliacaniales are more like a basal grade, connecting the older fern lineages with the younger, more recently emerged fern lineages. This evolutionary grade gives way to the Schizaeales, which also includes a variety of species. Although the variety in the Schizaeales is a little less disordered. They've been organized into 3 families: the Schizaeaceae, the Anemiaceae, and the Lygodiaceae. The Schizaeaceae are about 190 species of small tropical and temperate ferns, with thin stems and small leaves at the top. In a lot of species, the leaves look like little green combs at the top of the stem, which holds the reproductive organs. The second family is the Anemiaceae, which are larger ferns with a more traditional fern appearance that grow their leaves in a symmetrical dimorphic pattern. However, there's a subgroup within them, an African genus called Moria, which defies this dimorphic pattern. The third family is the Lycopodium, or the climbing ferns. These are tropical ferns that demonstrate indeterminate growth. As long as they have access to sunlight, water, and nutrients, they'll keep growing, forever. They have structures in their stems called rachis, which are long, flexible structures that act like grasping vegetable tentacles. The rachis will warp or curl around objects in the environment, like a tree branch, or a small protruding part of an artificial structure like a windowsill, a loose nail on a building, a rooftop, a deck handrail, gutters, whatever. If the rachis can warp around it and get a secure hold, then it will anchor the frond to the surface and hold it steady. The Lycopodium fern can then continue growing, literally climbing up the sides of a building, or up a tree and through the tree's canopy. They grow, climbing up until they find a new anchor, which they'll just latch onto to support more growth, so that they can climb higher into the air and better access sunlight. Branching fronds from these ferns can hang off of the trees or buildings and dangle their vines down to the ground. Some of these fern vines can grow up to 12 meters long, or 40 feet. After this basal evolutionary grade of the Gliacennules and the Schizaceae, the next lineage that diverged from the fern line was the Salvinules, or the water ferns. As the name suggests, these are marine-based ferns that live either rooted in the water-saturated soil of wetlands or the coast, or they live free-floating on the surface of the water. The Salvinules are also heterosporous, producing different kinds of spores, like a microspore that makes male gametophytes, and a megaspore that makes female gametophytes. Interestingly, this trait separates them from every other kind of fern. This was kind of surprising to me when I learned it, because I kind of assumed that for a whole group of plants that all reproduce with spores, it seems a little counterintuitive that only one clade within them would be heterosporous. I would have figured that it was a much more common trait among the ferns. After the Salvinules diverged from the main fern line, next to diverge was the Cyatheales, or the tree ferns. If the water ferns live in the water, then it's not too hard to guess where the tree ferns live. Except it might be harder than you think, because if you guessed that tree ferns live in the trees as the epiphytes, you'd be wrong. They're called tree ferns because they're huge, and they grow these thick, tree-like stems that can get anywhere from 1 or 2 to more than 30 feet tall. These tropical and subtropical ferns have really large fronds that unfurl through vernation just like the rest of the ferns. Each frond can be several feet long, with many of the larger Cyatheales ferns looking a lot like palm trees, like the Cyathea medullaris in New Zealand that can grow up to 20 meters tall and rakes the sky with huge fronds that look like giant green rib cages on long green spines. When the Cyatheales diverged, the lineage that they split from would become the Polypodiales. These Polypodiales are kind of neat, because in a way, they are to ferns what flowering plants are to seed plants. The flowering plants are the most recently emerged lineage of seed plants, and they account for the majority of the currently extant seed plant species. In much the same way, these Polypodiales are the most recently emerged fern lineage, showing up around 100 million years ago. And despite that, they're the most common, comprising something like 80% of the modern fern species. Where all the other groups have a single-digit number of families, like Osmundules with 1 family, Hymenophyllales with 1 family, Salvinules with 2 families, Gliacennules with 3 families, Schizaceales with 3 families, and Cyatheales with 8 families. Now if you look at the Polypodiales clade, by comparison, it has a whopping 26 families. Because they're so numerous, they're very widespread, having diversified to adapt to a wide range of habitats, generally excluding the more explicitly brutal habitats like boreal forests, hot deserts, and high up in the dry, cold, mountainous habitats. Where on one hand, diversification is a good thing because it allows them to adapt to a wide range of habitats, diversification can also be kind of frustrating because it means that there aren't too many traits that are shared among all of the polypodiales, and those traits that are shared are really deeply ingrained. They're chemical traits that exist at a cellular level. Specifically, the polypodiales share a consistent sporangia structure, with a similar arrangement of the spore-producing cells and similar morphology of the sporangia degradation that leads to the controlled release of the spores. You might have noticed this as I talked about other species in this episode, and the episodes on green algae and on mosses and liverworts and hornworts and stuff, but when you have a wide and diverse group of species that don't share that many traits, the traits that they do share will typically exist at a very base level, something like the structure or the arrangement of the cells and the reproductive organs themselves. Anyway, both the Usporangiate and the Leptosporangiate ferns exist within a massive overarching clade called the Polypodiopsida. The first ferns appeared some 360 million years ago, and for 40 million years they were the most advanced plants on the planet. But after this 40 million year period, where ferns were the tallest plants that existed, a lineage diverged that would become the spermatophytes, the seed plants. This lineage of the spermatophytes, which includes the gymnosperms and the angiosperms, will be the subject of the next few episodes in this series. If that sounds interesting, if you want to hear more about the Kingdom Plantae, then come back next week to check it out. I hope you had fun listening to this episode on ferns, and I hope you learned something cool about these quiet, unassuming plants. And if you thought this episode was cool, if you thought this was a quality thing to listen to, then be sure to give it a like and share it with your friends. And as always, thanks for listening.
Would you like to support the BioLogic podcast? It's super easy. When you open a new episode, press the like button or share it with your friends. If you aren't subscribed, you should hit the subscribe button so you can enjoy a new episode every week. You can also peruse our official store, which has a ton of cool stuff like hand-designed t-shirts, hoodies, and stickers. All the links you need are in the description section below.